started. Good afternoon. So thanks everybody for showing up to the Lockheed Martin Robotics Seminar Series. We would like to first welcome Professor Peter Stone. It's my pleasure to introduce him. Professor Peter Stone is a David Brutton Jr. Centennial Professor and the Associate Chair of Computer Science. And he has so many titles. I'm going to just read through everything. So he's also the chair of the Robotics Portfolio Program at the University of UT Austin. He's also the founder and director of the Learning Agents Research Group, LARGE, within the Artificial Intelligence Laboratory in the Department of Computer Science at the University of Texas, Austin. Professor Stone is also the president, COO, and co-founder of, I guess it's the
Coach Ty.
Coach Ty, yeah, Coach Ty Inc. That's his company. So he's very, you can see accomplished in all these kind of domains. And he's an expert in AI. So today he's going to talk about efficient robot skill learning. And we also would like to thank our sponsor, Lockheed Martin, for hosting this seminar. Thank you. So let's welcome Professor Stone.
Thank you very much for the kind introduction. I should also thank your sponsor for the symposium, because Lockheed Martin is a sponsor of my lab as well. So, so it's a real honor to be here. I've actually I've had close connections, several different close connections with University of Maryland over the years, but I've never actually visited here in person. So one of Dana's PhD students was a postdoc in my lab for a while. There's currently a PhD graduate from the ECE department here who's I'm doing joint research with, who's embedded in my lab. I'm actually going to talk about that in this talk. So I actually do a lot of different things in my lab, and sometimes when you come to when you give a talk like this one, you pick one thing and go really into depth and make sure everybody understands the details. I'm going to give a different kind of talk in this case. I'm going to give more of a high-level overview talk and give a sort of sense of all the different things that we're interested in my lab. The advantage of that is that if you're not interested in one of the things I'm saying, just hang on a second and you might get to something else that's more relevant to you. The disadvantages, of course, is if there's something that really does interest you, we may have to have a follow-on conversation or look at the paper for the details. But I'm very open to that. I'd love to hear comments on any of the things I'm talking about here. I am going to start with sort of overview. I am going to go somewhat deeper dive on two technical areas that are indicated here by this title, that are related to robot skill learning. And one of which, as I said, is collaborative with somebody who has a direct connection to this university. So, as I said, there's lots of things we do in my lab. The thing that ties them together is this research question, which really has appeared in almost all of the talks I've given over my whole career. It's to what degree can autonomous intelligent agents learn in the presence of teammates and or adversaries in real-time dynamic domains? And this is a very general question. It's really, but how do we create robust autonomous agents? It's sort of the one take on the grand AI problem. And so this has led us to do contribute to research in the autonomous agents community, the multi-agent systems, machine learning, especially reinforcement learning, and that's one of the things I'll emphasize in this talk, and also, of course, robotics, because I think it's important to keep ourselves honest in terms of when we're creating intelligence to also make sure that it's robust to the challenges of the real world. So we have in my lab both sort of what I call bottom-up, sort of algorithmic-driven theoretical research, and more top-down problem-driven research. If I'm giving a one-slide introduction to my lab, as I'm trying to do here, it's a lot harder to give sort of an overview of the algorithms, but I can give you a sense of the applications that drive us. And so some of the things I've been involved in over the years, the robot soccer competition. So these are some of our robots from about 10 years ago scoring a goal where they're having to sense, decide, and act. There's no remote control here, so they're doing vision, localization, everything together. This is a part of the robot soccer RoboCup community. I'll talk a little bit more about that on a coming slide. When Sony stopped making those Ibo robots, they moved to these Now robots made by Aldebaran, now SoftBank. This is a video clip from the 2012 finals where our team was playing against a university from Bremen in Germany. Ours are the ones with their hands behind their back, sort of the pink bands around their waist. This was the finals of the competition, so I'll just play this for a second till you'll see the first goal we scored. We ended up winning this competition when we went back to UT Austin. They lit the tower orange for us, which they usually only do when the football team wins. So, but it's important to remember here that, again, the robots are fully autonomous. So there's a lot of technical challenges to address to get to the point where the robot can walk up to the ball and kick it in off the goalpost like this. So that's one of the motivations for the more technical work I'm going to talk about later in the talk. Another project that we're, and again, some of these I could give whole hour talks on just these videos. This is another project that I'm engaged in, which I call the Building-Wide Intelligence. It has an acronym close to your airport here, so people always get confused about that a little bit, but it's our BWI robots, Building-Wide Intelligence. The goal here is for them to become a part of the social fabric of the building, for people just to not have to ask us for a demo and say, can we see how your robots work, but to just to come into our building, expect to see the robots wandering around, doing things that are useful to visitors or to occupants. This particular video is about some collaborative research with my colleague Ray Mooney, who works on natural language processing. It was about grounded language learning, where we did a week-long experiment where people could just type in open text to the language to ask it, to the robot to ask it to do things like deliver things or lead them somewhere. And over the course of the week, we were able to document that by learning from the dialogues where a person would say something the robot wouldn't understand and so have to ask questions about it. At the end of the dialogue, it would understand what the person meant, and then it could use all of the previous statements as training examples for the end meaning in a grounded language learning kind of context. By the end of the week, we were able to document that the robots were able to use shorter dialogues, complete the tasks more at a higher rate of completion, and people were less frustrated with the interactions. And so this is just one example of kind of the research that's driven by this larger project. I did also have a car in the DARPA Urban Challenge. This is relatively old at this point. This is our car in the back here. It has no person in it doing one of the tasks. So it had to find a gap in traffic and make a left-hand turn, and then come up to this line up here and make another left-hand turn. And it did 8 of those loops in about 20 minutes. This is one of the tasks in the Urban Challenge back in 2007. We don't have this car, this autonomous car anymore. As you know, all of the car companies are investing huge money in making autonomous cars. So our sort of one-off research prototype didn't have as much of a place anymore. But we still think a lot about what the world will look like when all the cars on the road are autonomous. I think that once that happens, that we'll be able to see intersections that look like this. This is more of a multi-agent systems concept. Rather than a traffic signal or stop sign, what's happening is there's a program at the intersection that's maintaining a reservation table. The cars that are white have called ahead to get a reservation to go through the intersection. The ones that are yellow don't have a reservation yet, so they have to stop. But once they have a reservation, they can move through with a guaranteed no collisions with the other cars. This is we put out almost 15 years ago now, and this was the initial concept. When all the cars were autonomous, we've now done a decade and a half of research on what happens if there's a mixture of human cars and autonomous cars. What happens if you scale this up to multiple intersections? What are some of the mechanisms for making the traffic flow more efficient? There's a fascinating line of research that has been spawned by this, and again, that itself could be its own presentation. So that gives you sort of the idea for the kinds of problems that motivate me. Just to dive a little bit further into the ones that are going to motivate the technical aspects of this talk, I'm going to talk a little bit more about RoboCup, the Robot Soccer initiative, because it really drives home the need for efficient skill learning on robots. And then I'm going to have a two-part sort of technical aspect, one on that falls into the space of simulation to real. So how do you learn skills where the learning is happening in simulation? You want them to apply in the real world. Inevitably, there's a reality gap. The simulation isn't perfect. How do you address that? So I'll talk about our solution to that problem. And then talk about some imitation learning from observation. How do you enable an agent that is trying to learn a skill, not to have to start from scratch, but to observe another agent that already has this skill, be able to use that to jumpstart its learning process efficiently. And I'll talk about two algorithms we've developed for that. So that's sort of the roadmap for where we're going. So with regards to RoboCup, this is a grand challenge for artificial intelligence. The grand challenge is to create a team of robots that can beat the World Cup champions by 2050. So, it's very ambitious, but, we still have 31 years to go, so who knows. I was actually 2 weeks ago at South by Southwest in Austin. I was on a panel discussion with Garry Kasparov, who is the human chess champion who lost to Deep Blue when the computer finally beat humans at chess. And so we had a nice discussion about the differences and different challenges in sort of a physical challenge at being better than people than a game intellectual challenge. Of course, there's been others like Go and Jeopardy. I'd say RoboCup has been going on for about 20 years now, so it's not super early stages, but there's still a long ways till this deadline that we've set for ourselves. There's really some really great virtues of it as a challenge problem. It's designed, it can really motivate incremental challenges, but where you can have a closed loop at each stage, meaning that even in 1997, when we couldn't come close to solving the vision problem or the action problem completely, you could still have complete systems that were playing some semblance of soccer. Now, if I look back at them, and I'll show you what it looked like, it's a little bit painful to watch. The robots were very slow. They were, they would fall over. These are 4 of the different leagues. So this is the early edition of the IBO robots. But when they fell over, they would get up. Sometimes they'd run into walls. Some of these robots actually caught on fire during the competition. But in 1997, it was a huge achievement just to have multiple robots in the room, all perceiving, deciding, and acting in a closed loop. And you could do that already at that point. If you jump ahead oops, what's going on? You jump ahead 10 years from that, still more than 10 years in the past, you'll see big improvements. So the robots are now much faster. They're able to do more collaborative things, passing. It was the beginning of the humanoid robot competition, so they just did a penalty shot competition that year. But even then, the robots could kick the ball. Now, if you look at this league, there's a lot more progress. Here, there's a lot more passing and fast motions. These are all videos not from my lab. This is a large community of people around the world, all sort of motivated by the common challenge of trying to get robots to play soccer. In my lab, we've focused a lot on the simulation league, and this will play a role in the talk. We've actually won the competition 7 out of the last 8 years. This is the 3D simulation league that looks where you have 11 agents on each team, and they have to they're being controlled at the joint level in an environment with gravity. So just getting them to be able to walk and without falling over is a challenge by itself. And then also there's the coordination problem. This highlight happens to be my student's favorite one. I promised him I'd show him this. It wasn't planning to do this, but somehow it managed to kick the ball through the legs of the other robot and score a goal. So he's always very proud of that one. My student Patrick McAlpine, he's graduated, he's now at Microsoft Research. His thesis contributed a hierarchical machine learning method for learning many different aspects of the skills that go into this, fast walking and kicking and positioning. So this, like I say, we'll come back to this later in the talk. I said we also do participate in the Standard Platform League. I said our goal is by the year 2050 to have robots that can beat people. Since 2007, we have had robots play against people in the competitions. This was the champion in, I think, 2011 of the middle-sized league, where the programmers always tell us, oh, you can't play against them. They're going to hurt you. They're way too fast. You get no chance. Here, myself and some of my colleagues showed that middle-aged amateur soccer players could still beat the robots. Every year we do this, it gets a little bit harder. We're not sure if it's because the robots are getting better or we're getting older, probably some combination of the two. But it is, it's interesting that we're at a point where we can actually put people on the same field and it doesn't look ridiculous. And, there's still huge challenges in getting humanoid robots that have the agility of people, and there's also the decision-making challenges. But it's been a phenomenal sort of progress over the year. If you're interested in these things and you haven't been to RoboCup, I strongly encourage you to come sometime. I'm about to be the president of the RoboCup Federation. This coming competition will be in Sydney, Australia, in July, and it's really a phenomenal event.
Do you allow agitation?
What's that?
Do you play soccer yourself?
I do.
You allow agitation?
So, the question, the rules of what should the, what should the robots be allowed to do is...
My grandson was a very good player. He goes to the other team and goes like this.
Yeah.
And he passes by.
Yeah, if that works, then the robots should figure out how to do that. That's, yeah, please.
Do we have a limit on the power that the robot can have?
So each of the different leagues, and please, questions are absolutely fine. Each of these leagues has different rules. So there's the standard platform league. Everybody has exactly the same robot, and it's just a matter of the programming. In the humanoid league, they've taken care to put sort of restrictions on it having a humanoid type body, so the feet can't be too big, the camera can only be forwards. In terms of power constraints, I don't think anybody has placed power constraints on at some point, yes.
If there are going to be humans and robots
On the same field and have it be safe.
there better be a limit on the robot power, or else the robots are going to win every time.
Yeah, so actually I have an article in a philosophy book where the question that we asked was, what would the rules of the game need to be in 2050 such that if robots win, that everybody, the general public, would agree that robots are better than people at soccer. And we use this as a way of asking, what's the essence of the game of soccer? Clearly, if people, if the robots, every time they get the ball, kick it 300 miles an hour into the corner of the goal, people will say, okay, but that's not really soccer. So now we went, and I'm happy to talk offline, we designed a set of rules, and it did include limiting things like that, like the speed of the robots and things, to try to make it so that people would agree that really is soccer that they're better at.
Because they'll win every sport there is if you let them.
Maybe. I mean, that's one, that's the optimistic view from a robotics perspective.
That is not going to happen the next 20 years? It's a public statement.
Yeah, it's I mean, there is a view that they would, they'll have superhuman capabilities, no question. But there's also the view that it's going to take forever to get robots that can actually run and move as agile as people.
Combined, the passing is the problem.
Yeah.
If you look at the best soccer teams, why they win is because they are very good in the passing, not because they can shoot 50 miles per hour. That doesn't work.
I apologize. One more comment.
Sure.
Take baseball.
Yeah.
It only takes two things to win. A pitcher who you can't hit and a hitter who you can't strike out.
Yeah, but those are harder to as a roboticist, those are harder to build than with a humanoid form than you would think.
You know why he makes this comment? Because he knows how to play hockey.
I see.
He doesn't know how to play soccer.
All right, let's take the rest of this conversation offline, but I'm happy to continue this at the end. I do want to say that as a part of RoboCup, it's not just about soccer. So the community has also engaged in sort of broader questions about multi-agent robotics. So we also participated in RoboCup at Home competition. There's a standard platform league using this Toyota robot, and where the robot has to be programmed to operate in a domestic environment, to be able to walk up to a table and to be able to pick up the items and put them back on the shelves, or help you unload groceries, or follow people through a crowded space. These are skills that are surprisingly difficult to get robots to be able to do, and RoboCup has a long-standing commitment to trying to get robots to be able to operate in this kind of domestic environment.
Is this a new competition?
Yeah. Yeah, so I would encourage you and your lab especially to check this out. The rule book is very aligned with the kinds of things that you're doing, and there's challenges exactly like I said. One of them from last year was unload groceries. There's a bunch of items on a table, and you need to put them away on a shelf where you have to put similar items near each other, but you're not told what it means for items to be similar. So the robot has to have concepts of, what does it mean to put things away in the right way. You have to open a dishwasher and put dishes away. Things that are skills that we want general purpose robots to have. So that's really, that's all up to this point, motivation, sort of the first third of the talk, the kinds of problems that really fascinate me and drive me, and that, by the way, I think are far beyond the capability right now of just throwing a neural network at it, right? There's a lot of hype right now about, neural networks and end-to-end learning from pixels to actions, but if you try to do this, play soccer or have a robot that's a general purpose service robot in your home, we're not even close to being able to just do it all with one neural network. Right? So this motivates sort of much more integrated artificial intelligence that brings together knowledge representation and reasoning, planning, multi-agent reasoning, and of course also learning for aspects of the problem, but certainly not end to end. And so what I'm going to do now is focus on an aspect of learning some of the skills that go into these tasks that I've been motivating up to this point. So and here I am going to go a little bit deeper, but again, for full details, you'll need to go to the paper or talk to me offline. The goal here is to do reinforcement learning on physical robots, and this is joint work with Patrick McAlpine, who's at Microsoft Research now, and Josiah Hanna, a PhD student who's on the job market, actually just got his first faculty offer yesterday. He's very excited. The goal here is that, the problem is that learning on physical robots, like this one, is not very, learning often in the reinforcement learning methods we have are not data efficient to just do all the learning on this type of robot. Plus, it requires supervision. If you want this robot to learn how to walk, while it's learning, it's going to fall over a lot. So you're going to have to manually put it back in place. The robot's going to break. There's going to be wear and tear, which makes the problem itself non-stationary. Learning in simulation has the advantage of you can do thousands of trials in parallel, no supervision needed, automatic resets, robots don't break. So clearly, that's what you should do. That's what everybody wants to do, is do the learning in simulation. The problem is, and this is what it might look like to learn a policy to walk with the ball or to walk fast in simulation, and we have methods for doing this. This was part of Patrick's thesis, which could be its own talk, but I'm not going to talk about the methods for that. I'll just tell you instead, if we take that policy from the simulator and put it on the real robot, it can execute, but here's what happens. It'll take 1 or 2 steps and quickly lose its balance and fall over. Now, why is this? It's because, well, the simulator is similar to the real world. It's not perfect. Now, the first thing you might say is, well, then let's improve the simulator. Let's make a perfect simulator, and then that'll solve all our problems. It's just, from my point of view, that's, despite all the efforts, we're never going to be able to get there all the way. That you can, there's always going to be some kind of reality gap, no matter how good the simulator is. And so what we've been doing in our research is a particular way of trying to accept that there is a reality gap and try to deal with it. So this falls into the general class of research known as sim to real, or transfer from simulation to real world, where you have some simulated environment and where you can do your learning. You want to move it to the real environment. The state and action and reward interface is the same for your policy, but the dynamics of the simulation are not the same as the real environment. And so there's, like I say, there's some work on trying to just transfer the policy directly. Inevitably, that doesn't work. There's a line of work on making the policy or the simulated environment more noisy, so that you're forced to learn a robust policy, and then that will make it more amenable to differences in the environment. There's been some success with that, but it doesn't go all the way. There's also been approaches that take the experience in the real world and use that to build or improve the simulator. And it's sort of in that class of methods that our approach falls, but it's got a particular unique take on it, which we call grounded simulation learning. So the main idea of grounded simulation learning is that you start by executing your policy in the real world. You then take those real world trajectories to ground your simulator, and I'll say what I mean by that in a second. Then you take that, but what it means at a high level is the grounded simulator is more similar to the real world than the initial simulator. You then take that grounded simulator to learn within that grounded simulator, take the improved policy from that, execute it in the real world again, and then relearn the simulator grounding. Okay, so we're not actually going to change the simulator itself. The simulator will be taken as a black box, but we're going to learn a wrapper around it that makes the policy more similar to the simulator, or to the real world, at the current point in the search space where you're searching. So it might actually make the simulator worse as a whole, but in the local region where you currently are in the search space, it'll make it more accurate. You'll take a step in that direction and then relearn a new grounding of the simulator. So diving into a little more details on how we do that, what we mean by simulator grounding is we're now going to take this policy that is, what is a policy? It's something that takes in the current state and outputs an action. we're going to be learning walking, so just to get you thinking in the same way, a policy in this case is what joint angle should each of the 20 joints or 20 or 30 joints on the robot go to at any given time. So you could say move your knee joint to 90 degrees, and then the next step move it to 80 degrees and 70 degrees. What's the action that should be taken? And the reality gap at its extreme is that, like, say I tell this joint in the simulator to go to 90 degrees, maybe your simulator has instantaneous dynamics and it goes there immediately. Clearly in the real world, if you say go to 90 degrees, it's only going to go part of the way. So the question we want to answer is, when our policy says go to 90 degrees, what should we replace that command with such that it goes to the same place it will go in the real world if you said go move 90 degrees, right? So that's what it's going to mean to ground the simulator. The way we do that is going to be by learning a wrapper or a modifier to the action that comes out from our policy.
You cannot put that into your model. The example you
So we could. So you could. Oh, if you have the access to the simulator, you can open it up and change the dynamics. This is assuming that we don't necessarily. This will work even if you don't. The simulator is a black box. It's object code or something like that. This is just. And that's a good question as to whether that would work better or not. But this is a fully general method, even if you can't access the internals.
You cannot do that if you assume that you're totally agnostic, right?
What do you mean if you're totally agnostic?
There are models behind your simulation.
So this doesn't require. So this is going to basically assume that we don't know anything about what's in the simulator. If you do have the models, then you could go in and change them in a way very similar to this. So you could actually then go in and modify it inside the simulated environment. So you could also just think of this G module that I'm going to tell you how we learn going inside the simulator in your case. Yeah.
So here's a dumb application of that. Take your example. Right, in the time you allow, you command 90 degrees and it goes 30.
Mm-hmm.
So that says command 180.
Right.
Well, but that's a nonsense command, isn't it? I mean,
it's going to be the opposite. Instead of the command that we said that would go 90, it actually goes 30. So now we want to say instead, let's figure out what command will make it go 30 in the simulator. So that'll be 40, right, or 35 or something like that, right? But so yeah, but you could get in a situation where the command, well, so we're gonna use a learning method that'll find the best command to achieve what we're trying to do by learning this function G, which is basically going to replace the robot's action with an action that produces a more realistic transition, and learn that as a function from of the state and action. So going into detail, the transformation is you have the state, you have your action, you want to figure out what action to replace that with. So instead of the 90, I want to replace it with the 35, for instance. So we're going to do this by first learning a forwards model of the real world. So F here is a function that says, if in the real world I was in this state and I gave this action, what next state would the joint end up in? And then we're going to learn an inverse model of the simulator that says, if I want to get from this state to that state, what action do I need to send such that that will happen? You compose these together and you get this, the internals of our function G, and then you can do that for every one of our joints, right? So, and then basically if you've learned this F and F and this forwards and inverse models correctly, then you should get the simulation commands giving you more of the transitions you would get in the real world. How do we learn the F and the F inverse? We use a neural network. That basically in one sweep will take your current state, your current action, a label of the predicted next state by having some ground truth trajectories from the real world. So we can have a fairly small number, 15 real world trajectories of 2,000 time steps each. So it's 15 times 2,000 transitions. And then the inverse model, which is your state and predicted next state to the transformed action, we train on 50,000 steps, which is just 50 trajectories from the simulation. Once we've got this neural network, we put it in, and we can do some experiments and say how well does this work. So we actually have a real robot. We have a sort of high fidelity simulation and the lower fidelity simulation. So we can do experiments from either of these to the real robot or from the low fidelity to the high fidelity. That's the more practical way to get lots of data. But what I'll tell you, in the paper we have all the details of this. the main punchline is that we started with the state-of-the-art walk on these robots. It was one from the University of New South Wales that they made available, one of the top RoboCup teams. For the learning in the simulation, we used a stochastic search method known as CMAES. That was the subject of Patrick's thesis. But then we were able to take that walk, and this is what it looks like. This is the initial walk that we got from UNSW. It's moving 19.3 centimeters per second. And then using this grounded simulation methodology, putting that walk into the simulator, grounding the simulator and learning, it was able to improve it by almost 35%. This is what it looks like. It's actually sort of squatting a little bit lower. We then gather more data at this point in policy space, reground the simulator, and we ended up with the fastest known stable walk on this robot, which looks like this one. And so this was going 28 centimeters per second. And so there's now so this was sort of a validation of this grounded simulation learning method. And so that's the high level. The punchline is that it improved the walk speed by over 40% compared to the state of the art. It became the fastest known stable walk on the robot. Of course, it also opens up lots of questions. So, how will this methodology work on other robotic tasks and other platforms or other non-robotic tasks? So with one of our industry sponsors, we're working on a control of a chemical processing plant where they have a simulator that doesn't perfectly match reality, and they're interested to see whether this can help their performance. Also, just when does the grounding actions work and when does it not? We're getting some more insights on that, but this is still ongoing research. The main paper was a AAAI 2017 paper. Yes, please.
Is it possible you could have gotten the same result by having the robot just vary its center of gravity over multiple walking trials and then pick the one with the best performance?
So that's in some sense that's at the very high level the way the learning process works in simulation. So we're using a CMAES. Basically what it does is we have a parameterized walk, which is basically varying the center of gravity, the stride length. It uses a double inverted pendulum model, so it sort of swings the center of mass over the foot as a fulcrum of a pendulum, changes to a double support phase, then does the same. That opens up a whole bunch of parameters like, how much should the body sway, the center of mass move back and forth, how fast should it go, what should the stride length be. Those are the parameters that are being optimized in simulation, in the simulation part of this loop. But to do that, the search process tends to take, I have statistics on it, I think if we did it on one computer, which is moving much faster than in the real world, it would have taken 1.5 years of simulation time to get from our starting walk to the final walk.
Do it with physical robots.
So to do it on the physical...
Pick some intervals of variation
Yeah.
for the center of gravity and run those end trials and then pick the one with the best performance.
So
It's kind of a backhanded way of asking, why can't you get the robot to stand fully erect with a higher center of gravity and move faster?
yeah.
Isn't that
So in my past research using the Sony Ibos, which I showed the dogs before, we did do learning that was all on the robots with no simulation. And in about 3 hours, they got to the fastest walk that anybody had made the Ibo work in. Again, within a parameterized space, using sort of the method you're doing. It just tries a bunch of random perturbations, then picks it's a little more complicated than just picking the best one. It sort of moves in estimates the gradient of this search space, moves off in that direction. The thing that makes it more challenging on the humanoid robots is on the quadruped robots, if you have a bad policy, they're still stable. These robots, they just, if you just take random sort of perturbations, they're falling over all the time. They're breaking. It just wasn't viable to get enough training data, and it's a much more complicated dynamics problem. We have it rather than a 12-dimensional parameter space, we're at the more 30 to 50 dimensional space, and so we sort of got to the point where we couldn't just do this all in the real world in a scalable way. So that's.
Find the solution analytically? Is that what you claim?
Yeah, I don't think you. I mean, I can't prove that you can't find it analytically, but there's no good when you're doing the ground contacts of with the robot. There's enough noise even if we suspend the robot in air and just move the joints according to a control policy. There's enough noise and uncertainty in that. Once you get contact with the ground.
Bus control methodology for nonlinear systems?
It'd be great to see. I mean, I think that's basically the approach that was the starting walk, right? So this to get to this walk, which was the state-of-the-art walk before, was more of a traditional analytical approach based on one of these inverted pendulum models, and there've been people who've used ZMP models and things for humanoid in the traditional walking methodologies. That was our starting point, and we were able to learn to improve that by 40%. Maybe it's clearly that it's possible to do better, because our policy is still in that space, but I don't think it would have been very easy to find it. It'd be great. I mean, if somebody wants to take, these robots are publicly available. If somebody can take them and improve them.
The way we do these problems here, at least with me and my students, is we treat these hybrid automata of high complexity, and we know that they fail only because a small part is the problem.
Yeah.
And that one you can solve. You don't have to do the whole thing. And the problem I have with the simulation is you're hitting the whole robot.
Yep.
While the problem is in only a small part of the dynamics.
I think when it comes to walking, it's the complex interactions of all of the different motions, the center of gravity, the contacts with the ground. It's the walk. By the way, the walk that we learn doesn't work well on one carpet versus the other carpet. We're going to have to retrain, or so it's your analysis is going to have to take into account
What's happening is something that's called trusted autonomy today. Is that you're trying to have a model of the motion analytically, and then you try to have a self-monitor and self-adjusted mechanism for all the components of the system.
Yeah.
And this has produced very, very good results.
So let's talk about this afterwards, because I'd be interested to hear more. Let's talk about it offline afterwards. I think it would be an interesting to compare what could happen. I should say, one of the other things that this does motivate a lot is in the reinforcement learning literature, off-policy evaluation and safe learning. How can you make sure that during the learning process the robot doesn't fall over? How can you take data from one policy and have it applied to learning in another policy? That's joint work that we've also done, and we've had at ICML and AMOS in the years afterwards, very much motivated by this. In any case, in the interest of time, I want to shift gears to the other method that I want to go into a little bit of detail on. Like I said, imitation learning from observation. And this is joint work with, as I said, an alumnus from University of Maryland, Garrett Warnell. He was Rama Chalapa student. He's now an employee of Army Research Lab and is embedded in my research lab. We jointly supervise my PhD student, Faraz Tarabi, and together we've come up with two different approaches, new novel approaches to imitation learning from observation, one model-based and one model-free. So I'll tell you what I mean by that. So the goal here in this work is to learn how to make decisions and learn skills by trying to imitate another agent. So conventional imitation learning is you get observations of the other agents which consist of state action pairs. So for instance, in this video, there's a person giving sort of kinesthetic demonstrations to the robot, saying, here's how you check this box. This is Scott Neekham's research. And so the robot can track the states it goes through and also the actions that it was taking, how its joints actually moved. Our challenge here, the challenge is that precludes using a large amount of demonstration data where you don't know the action sequence. All you do is you observe the state sequence. And so from YouTube videos, you can see other agents moving, but you don't know what actions they were taking. Now, I'll talk a little more about that, but in the large space of imitation learning, there's two general approaches. There's behavioral cloning, and the idea of behavioral cloning, which has been used for applications such as self-driving cars, is you take a demonstration policy and try to learn what is the mapping from state to action that the demonstrator is using, and you try to copy that. That's sort of at the high level. And then there's also inverse reinforcement learning approaches where the idea is that you observe the demonstrator, try to induce what reward function they're maximizing, and then learn a policy to maximize that reward function yourself. And so there's methods such as guided cost learning, generative adversarial imitation learning. The two methods I'm going to talk about are going to be one from each of these two spaces. So our goal here is imitation from observation, learning how to perform a task given state-only demonstrations, as perhaps this bird is doing right here, right? Actually, people have told me that it's not clear that the bird is copying the people. It might be the people is copying the bird, but either way, there's some imitation going on here with just seeing the states that the other agents are going through. You don't know what actions the bird is sending to its joints, or the bird doesn't know what the actions are being sent to the person. So our goal is to learn how to perform these skills in a situation like that. So we're given a demonstration of states, and we want to learn what is the policy that's mapping the states to actions that led to that sequence of states. There has been some other work in this space as well. As I indicate here on this slide, the commonality they have and the thing that differentiates it from what we're doing here is that they mainly focus on the perception side as opposed to how do you learn the policy. They're trying to align what is the sequence of states that are going through, and they require time-aligned demonstrations. So what that means is, you have to, if you have two demonstrations of that bird jumping, they have to be aligned in time, because they're basically saying at exactly this instant, where should what action should you take in exactly that instant. And that actually breaks down if you have cyclical motions like walking, because you get to the same position multiple times, and you can have it can be difficult to break, to disambiguate when what the time alignment should be. So in our case, I'm going to talk about two different approaches. One, a model-based approach, where we take the traditional imitation learning methods like behavioral cloning, where you start with a demonstration of state action pairs, but now we're not going to have access to those actions, and we're going to do a prior inference step to try to fill in what were those actions. So how do we do that? We'll have the agent sort of explore in its own joint space to learn an inverse dynamics model, then use that inverse dynamics model, which basically is a model that takes state and next state and infers the action that caused that transition, to fill in the missing actions, and then do conventional behavioral cloning. And so what that looks like is you have a policy, you run that policy, you collect your data, you update your model, you then get a new state-only demonstration trajectory, infer the actions, and then update your policy to try to match that the state action sequence. Yeah.
I'm sorry, but could you translate some of this into words that somebody like me might understand? The state and the action mean exactly what?
So again, think in terms of state as the joint angles currently of all of your entire body, and the action is what motor torques to send, or what action to what commands to send to the joints.
But in mathematics, the state would include the angular velocities.
Yeah.
At all the joints. So is that included in your data?
So that depends on, like in the general method, that's going to depend on what your robot is and what matters for the dynamics of this. So this is in general. I actually I'd have to ask Faraz what in this case I'll show you the results. These were done in the Majoku simulation environment. I believe that the learning was done just from the positions. But yes, if the angular velocity is a first order influencer in that transition function, then you would have to model it to make this work.
Of course it is, especially for stability, because it's going to change where the center of pressure is.
Yeah. So in this simulation, and again, I'll have to talk to Faraz, who did the implementation, but
The question is aimed at the inverse problem.
Yeah.
Because if you have what I would regard as the full state, then the inverse is not computable. There is a whole family of possible inverses.
Yeah. So I mean, we're going to again use a neural network method. So we're going to use a learning method that's going to be given training data and learn the best function within its policy class. That'll so the robot as it's collecting its data, it's just going to get state, next state, action triples, and it's going to try to learn using a conventional machine learning method, just try to minimize the loss in the prediction from a holdout set. And it's not necessarily going to be the only it's not going to get the right actions necessarily, or the only actions, but it's going to get a generalization based on the training data. So it's a learning-based method.
It's going to be extremely dependent on the person you observe and the robot itself.
Yes.
It depends on the dynamics of the person.
Yeah, absolutely. So that's the point, is that you have to learn from the.
Why don't you abstract something that we do here? Again, I'm not trying to be an adversary, but why don't you try to understand the logical model of the task, like a time automaton or something, which you can, and then, assuming that the robot has its own embodiment that it knows, which is not a bad assumption, and it has sensory input. Do your planning with these inputs, and bingo, you learned it. And with some of these, that works.
Yeah, so I mean, there's multiple methods. I'm not trying to say that this is the only way our interest here is trying to be able to observe a behavior and imitate it.
Sensitivity to the actor that you observe and your own dynamics is going to be a problem. Because if I'm going to go do it again for a different robot or observing somebody else, what can you say for that?
So then you're going to need to get, you're going to learn, yeah, you're going to do this again. So this is, so I mean, if you're trying to imitate the other one, then you have to do it again. If you're trying to, the point here is if you could either learn by doing it all from scratch. So, there's multiple approaches to having control. You can do it all analytically. You can learn from scratch without any starting point. I would say that there are situations where you can do it analytically, but I think there's limits to that. I think you can learn, there are situations you can learn from scratch. There's limits from that. This is an approach where we want to do learning, but we want to be able to do it in a data efficient way. So you don't want to start from random policy. You want to start from an imitation policy. It's one way to get a behavior into the agent. If your objective is just to get the ant to walk, you just need to see one demonstration, and then that can, or one set of demonstrations from one policy, and that can get you to a place where you can then improve it if you want. If you want to try to mimic different policies, then you'll have to start over to mimic the second one. It depends what your objective is. Are you trying to match the observed behavior or just get good walking? If you're just trying to get good walking, then you can ignore the future demonstrations you get. So, in any case, the testbed environment for us is one of these Mujoku domains. As I just showed the video of this general methodology that I presented, we can compare the performance of the demonstration policy normalized to 1 here on this graph, the random policy normalized to 0. The fitness function here isn't actually just speed, it's also how close you are to the demonstrations in joint space. I'm going to show first some of the existing methods for behavioral cloning. One of them, feature expectation matching, does particularly poorly on this domain, and that's a known effect for that algorithm. Gale and behavioral cloning, traditional behavioral cloning, all of these methods take state action sequences, so you know the actions of the demonstrations. Our method here, which I am adding into the graph next, has the handicap that it only sees the state sequence, and yet is able to do competitively with these existing methods. We can then sort of augment this method to say, what if rather than learning your inverse dynamics from a random policy, learn from sort of motivated, but similar to what I talked about in grounded simulation learning, learn from the current place you are in policy space, and update the model with that learned policy. We can then introduce this alpha parameter which controls that trade-off between performance and environment interactions. So when alpha is 0, that's what I've described so far. You don't get any post-demonstration interaction with the environment. When it increases, you get more and more. So the change is that rather than this diagram that I showed before, it closes the loop and said after you've learned this policy, run that policy, get more demonstration data to relearn your inverse dynamics model and continue in this way. So the behavioral cloning that I've shown so far has lots of pre-demonstration data, but then nothing after the demonstration is shown in white, and then you learn your policy. The existing methods get all of their interaction after the demonstration, and then BCO alpha allows you to control how much post-demonstration data are you going to get. Now, I will say we do have to use a lot of data in the pre-demonstration phase. So think of that as the robot when it's back in the warehouse learning its inverse dynamics model. But then once it gets the demonstration, the learning is very quick. And so now if we vary alpha in this setting from 0 shown in green to a higher value and then have intermediate values, you see that as we get more and more post-demonstration data, the performance improves.
What's the performance measure?
The performance measure is normalized so that 1.0 means the speed of the demonstration policy, and 0 means the speed of the random policy. So think of it as, like I say, it's not exactly just speed. It's a 4-dimensional reward function that includes speed and faithfulness to the actual positions of the joints over time. full details of that are in the paper, but it's basically how well it's walking. And then just briefly, I'll talk about our second approach to this problem, the model-free approach. Rather than building this model and learning the inverse dynamics model, we use a method known as general adversarial imitation from observation. So this is starting from a random, this is motivated by the, again, this observation that the distribution of transitions you see from a random policy and the distribution are distinguishable. These graphs are just four-dimensional graphs, 3 axes, and then the fourth dimension on color, on a particular showing the state and next state transitions for just 2 joints in the Hopper domain. And it just is showing that there's a different distribution of transitions from these policies. And so that allows us to be able to use one of these sort of GAN-style methods that's been very popular in recent days, where you have a demonstrator that's that is a discriminator shown in yellow here that's learning to predict the state next state transitions of the demonstrator. So if a 1 gets output from this network, that means this was a transition that you did see from the demonstrator, and a 0 would mean you didn't. And then on the imitation side, you learn a generative policy, which is shown in green here, a controller that's taking the state, outputting an action. That state in action gets sent into the environment, and then this is can get sent through that same discriminator, and the discriminator is trying to tell the difference between the state transitions that were generated by our generative policy and by the demonstrator. And so the discriminator is trying to tell the difference. The policy is trying to learn a state's trajectory such that the discriminator can't tell the difference. So that's what makes this an adversarial network. And then in the end, you get a policy that gives you an indistinguishable state transition profile from the demonstration profile. And so when we do this, again, we can compare against existing approaches that use triplet loss and these existing methods. Again, 1 is the demonstrator, 0 is a random policy, and our method, GIFO, is able to do almost as well as Gale, which again has access to the actions. And our method is only going from the state distribution as it goes. There's a bunch of, so the challenge is addressed here, just to wrap up. The states are not fully observable, the states aren't Markovian, so the solution, this is, all of that I was talking about, if the state, as you asked, the question was the actual joint angles. In general, when you're doing it from observation, you're actually going to have a visual demonstration. So in this case, we can do the same kind of method, but now use a convolutional neural network from image space to do exactly the same methodology. So now we're going to stack 4 frames from the input policy, use a convolutional network, and again, here's the discriminator between a policy our generative policy and the demonstration policy that's trying to distinguish the actions that are generated by the 2 of those. So you take exactly the same methodology, but now using visual input as state instead of the actual joint angles. And so, and here, this is in this Hopper domain where the input to the agent is just exactly these pixels. That's the demonstration, and here's the learned policy that came out. Looks fairly similar again and is effective. Just graphically, again, we're here showing this is the trained, 1 now is the policy that's by the demonstrator. The dashed line is using a TRPO, so a method that's also only learning from the visual state, but now using trust region policy optimization. And so it's sort of the expert policy from visual pixels. And then we're able to do better than any of these other methods and do actually as well as TRPO by with only seeing the state transitions as our input.
Yeah.
So that's a problem with an analytic solution.
Your state transitions have no timing, right?
That's right. So this is the state. They're on a clock. So a state transition.
You're only doing next, right?
That's right. This is all next state. So yeah, this is not. I mean, we could. It would be a complication that you could do perhaps to learn to model it as state, next state, and time elapsed. So you could add that. But this, we're just assuming it's on a fixed clock.
But you really could solve that problem analytically. It's easy enough.
To what? To
solve that Hopper problem with it analytically.
yeah. Yeah, so this is a test bed to test the method. It's
You can solve it analytically, you can solve it numerically for sure, and you can even solve it numerically with tolerances. This is exactly what you need. Okay, so I mean, forgive me for being questioning that regard, but we cannot forget physics, all right?
yeah. I'm not.
I've had these arguments with people that they argue about learning. There has to be a judicious combination of learning with physics.
Absolutely, I'm not arguing against that. In fact, I should emphasize. I hope this was clear that the underlying representation that we're using is still a physics-based model. We're learning the parameters of the physics-based model, which is I agree very much that you shouldn't try to learn everything end to end. You should try to learn the parts that you would have to. You should program in the parts you know how to do, and you should learn the parameters that would require difficult manual tuning or trial and error. That's exactly what this approach is doing, especially the grounded simulation learning. It's a physics-based inverse dynamics inverted pendulum model that we're starting with, but there's still it's not magic. How do you tune that? Just like a PID controller is a wonderful method, but to tune just the 3 gains on that is a lot of effort. So, I think there's a role for modeling and physics and analytics, but there's also a role for learning, and that's what we're focusing in on and studying in this case. So I want to be respectful of time. Let me just I'll say in this case we are also testing the algorithms on more domains, trying to adapt to physical robots. And also applying this to sim-to-real transfer using the algorithms. But again, this is the Imitation learning summary. We did a model-based version, a model-free version, and trying to approach the kind of skill that even babies have at imitating. And this is just the kinds of things where they can just see the pixels and yet very faithfully imitate the actions. So. It's actually a great video, but I don't have time to show you all of it. So, so with that, I'll just I'm happy to stay around and answer any questions about any of the things I've talked about here. But just to pop back up to the top level, the thing that connects all the research that I do in my lab is this question: to what degree can autonomous intelligent agents learn? And I focused in on the learning part in this talk in the presence of teammates and or adversaries in real-time dynamic domains. That's the multi-agent systems component, which I talked less about here today. But there's, that does appear in all of these things, in robot soccer and autonomous driving and in the human interactive robots. So with that, thanks for your attention. I'll be happy to take questions.
Let's maybe have 2 questions from the audience.
I have one question.
How about 2 questions from a different corner of the room, and then if there's time.
If we don't have any questions.
Somebody's got a question. Yeah, I'm sure.
So with imitation from observation, can we use completely different robots and use them, use one to learn from another how to do a certain task?
So that's known as the model mismatch, or where the demonstrator has a different physics than the different shape. That adds a greater challenge to the problem. That's one of the advantages of this, though. Like the crow and the people, they have this sort of body mismatch. So behavioral cloning from observation, that you can absolutely use the method, because the pre-demonstration learning, the inverse dynamics model, is done on your own body, and then you want to try to learn the mapping. Try to come up with the closest mapping for the demonstrator, and that doesn't matter what it is. It would be more challenging in the GIFO case, but that is something that we're looking at in ongoing research. So yeah, that's something. It's a good point. I should have emphasized that. Here, the results I've shown were all on observing an agent that has the same body as you in the same joint configuration. But yeah, in general, these methods can apply. It's just it's a little more challenging. Yeah.
So during the RoboCup, and so how do you kind of guarantee, or maybe from observations in the RoboCup, that once you have learned these policies, things are not going to, it's not going to fall down. Things are going to be in a stable regime.
Yeah.
How do you kind of guarantee that?
We don't. You can't guarantee that. How do you guarantee that you're not going to have an accident when you drive in the car? You're in your car on the road, right?
You can actually, right?
Well, there's
With this method, but you can.
No, what I mean is, let's say restricted domain. No other. They're just running around.
in ideal conditions, yes. But when there's other robots pushing you, and the carpet and the ball and the robots do fall over, and yes, there are formal methods-based approaches to this, but they all make assumptions that don't hold in the real world, and so Yes. So we can't guarantee, and any more than than we can guarantee, than we can guarantee that a human's not going to trip as they're running. I mean, this is a dynamic world, and it's not constrained. We're trying, that's one of the sort of the exciting challenges about trying to put this to the test in the real world, is that sort of you're out of the playground, you're out of this the sandbox. You have to deal with the real world complexities. And I would submit that if you want to only use methods that you can guarantee will work, the robot will stand still, right? As soon as you have the robot moving, the guarantees are going to be off.
Can I ask one question? I'll go to the last picture you showed the babies, all right?
Yeah.
Okay, so let's learn something from there, right? Why is it a bad idea to try to do what we do always in engineering, divide and conquer? Meaning, I know my embodiment. The baby knows how to move around from many years of time. He does, when he sees the picture, he shows a logical description of the task, and he does it. That's what I'm trying to get.
How do you know it's logical?
Yeah. How do you know it's illogical?
Forget the logical. Okay, what I mean is he shows a picture which is an abstraction of what he wants to do, right? The picture doesn't show him the kinematics or nothing. It shows him do that, and then he does it. Because its kinematics is already he knows.
I mean, in some sense, that's what's happening in behavioral cloning from observation method, too. We're having the motion inverse dynamics model being learned prior.
Do you have any objection to assume that the robot knows its own embodiment, right? But if you assume that, a lot of the questions that Bill Levine was asking, a lot of the questions I ask you, go away. Then the problem.
I don't think they go away. I think you can. I think they.
Because basically, then what do you say? If I look at the picture, I'm trying to understand. I want to go on top of the other baby. That's a pictorial description of a task. Then I take that task. I take my sensing and my own kinematics. I execute a planning, and I may be able to do it. That's all.
I think you can you can do it under constrained conditions. I think if you want to be fully robust, I think yes. I think there are, like I say, I think there's a place. I'm definitely a big tent AI kind of person. I think there's lots of different methods. And robotics. There's lots of different methods that we should be fully exploring. And I'm not telling anybody not to. If we can solve a problem with a fully modeled physics-based approach, then that's fine. The role for these methods, but I don't think that's going to solve every problem. I don't think, can you create a robot soccer playing robot that can beat the best World Cup champion using exactly that method? We should go as far as it can go, and then let's see where the learning.
What I'm saying so that you don't get the wrong message.
Yeah.
I think we need to combine model-based approaches with data and learning in an efficient way.
I agree.
Not just hit it all with learning.
I agree.
And put
That's.
it in CNN and then something's going to come out of it.
I said that very explicitly right at the beginning. I think these domains are exactly, the soccer and RoboCup at home are exactly situations where you can't do everything learning end to end. What I'm focusing on in this talk is learning very, very specific components, but I'm not saying that this is going to go to do the whole task. It absolutely needs to be combined with other methods, and I'm the first person to say that. Good.
At least on
On that point.